Welcome to Securing Container Workloads on AWS Fargate. My name is Theo Salvo. I'm a Technical Account Manager with Amazon Web Services. Today we're going to take a look at a few different topics around container security in Fargate, starting out with images and registries, looking forward then towards network security and authentication and authorization. Then we'll take a little bit deeper in the stack on runtime protection and take a look at some advanced features that are available to us. To start, it's important to remember how we got to containers and where this concept of containers and isolation comes from. The first container that was actually built was called chroot or change root. This was back in the 1979 based on Unix version 7 and gave users and administrators the ability to have jails in which only a certain user could access a certain set of files. This was thus made a little bit more popular when LXC was launched in 2008. This was an OS-level virtualization stack, which allowed for running multiple isolated Linux systems that all shared a single kernel. Of course, this was not made popular until Docker debuted at PyCon 2013 with a mainstream adoption of containers. What really led to this was the ability to have a single API in CLI with one-line commands that made it easy to consume containers. And while Docker was originally based on the LXC runtime, it eventually created its own runtime as well, which is the runtime that we're most familiar with today when talking about containers. So let's dive right into images and registries. And before we do, I want to make sure we all understand the concept of where an image comes from. When we talk about a container image, we're talking about images that are separated by tags, optionally stored in repositories, and are organized in registries. This is the format you will see whenever you're referencing any type of an image. So let's break down the example of nginx. Where does the image nginx come from? Well, nginx is clearly the name, but if we do not specify a tag, it will automatically get the latest tag. Likewise, it will also use the default repository of library and will automatically assume that you are asking it to go to Docker Hub and pull that container. So when we build an image, we want to make sure that we're starting with a known base image. Ask yourself these questions. What base OS did this image use? What repository did the base image come from? Who published it to that repository? When was it last published? And where or which registry did this repository come from? If we go back to our nginx example, let's take a look and see if we can find out some of these answers. If we look on Docker Hub, since that is the default for starting, we see that the nginx is listed here, and it does have a latest tag, which tells us that is the latest version that we have, and that's the default that we are going to use. Now, if we click that link to the right that says mainline stretch Dockerfile, we can see that this takes us directly to the Dockerfile, which specifies the base image for the nginx image is in fact a version of Debian running stretch and has been slimmed down for portability. This does, of course, beg the question, where does that image come from? And where does the image before that come from as well? When selecting a base image tag, it's important to avoid latest tag on images, especially for production workloads. Base images that are latest can sometimes introduce security flaws and can also trigger pipelines to suddenly fail when they may have been passing. So it's important to make sure that you are manually advancing the tag on your images or simply switching to using the digest, which specifies a specific commit during the image creation process. Once you use a defined tag such as nginx 1.13, and then when you're ready and finally ready to move up to 1.14, changing that inside of your pipeline, which will automatically configure the next build. This gives you a chance to catch any operational errors and ensure that you're security compliant before moving this into production. Or of course, you can start with what we call a from-scratch base image. A scratch image does not contain any files. It is completely empty of everything except for a bootfs from the curl, giving you a /root prompt. This means that if you want any particular utilities inside of your application, you have to put them there. And this helps to reduce the attack surface for what you're doing. A good choice for programming language inside of a from-scratch container is Golang, because Golang will package all of the objects and stack it as a binary into a single file. This means you can simply upload your binary file to the container and run that from your entry point in order to get into your container. Now, of course, when you're creating your Dockerfile, it's important that you make sure and specify user, because if you do not specify a user, your containers will run as the same user as Docker. This means root, and we all know how devastating that can be. So please give your container a user. Liz Rice, back in KubeCon Europe 2018, told us that she had done a study of Docker Hub, and she had found that 86% of images did not have a user line and were therefore running as root by default. Now let's take a look at how we can build some containers in our secure manner using the things we just learned. To start, I've built up a little bit of a demonstration environment. In the top right, I have a recurring pane that will show all the currently running containers inside Docker on my local machine. And I've also built in the top right a process watcher that will keep track of all the running processes on the host. Ideally, when you see me start a container, you should also see a matching process run, and that's how we can tell things like which user our containers are running as. To start, let's take a look at some of the files that we've curated today. Just have a few demonstrations here, and they're just labeled 01 through 04, and 02 has 3 different ones. And also, I've went ahead and preloaded some of the base images that we're going to use today, just so that we can keep track of them. These are, for the most part, all available on Docker Hub. The curl is a special one that was designed just to run curl commands and doesn't have anything else in it. So let's get started. Take the example of I want to have a static website running, and we're going to run it with nginx. To start, I need to make sure I craft a website. All right, done that for us here, and it's very simple. It says My Demo Page in both the title and in the header. Very simple. Let's get this up and running. In order to do that, I need a Dockerfile. So we'll start with a very basic example of just saying start with an nginx container. I'm going to copy in a special configuration that I have for nginx, which is going to cause it to run on port 8080. And I'm going to copy in everything in my source directory, which right now is just our index.html. I'm going to put that into a folder specific to nginx container that says, I will look for your website here. Lastly, I'm going to tell everyone else that I want to expose port 8080 so that they're aware that's the port I want to use whenever we launch this container. So let's get started. Let's go ahead and build the image. We're just going to name them all demo, and we'll tag them with 01 through 04, depending on what we're working on. As you can see, because we preloaded the images, that was done pretty quickly. Let's go ahead and get this running. We're going to name the actual container demo_01, and we're using the container image demo with a tag of 01, which is the one we just created. We've run that, and now we can see in the bottom right we have demo01 running, and it created 2 processes. Note this is by default the way that the nginx container works. We should see 2 processes here. So to verify that we do have our website, we're just going to do a quick use of our curl container. We don't need to stick around afterwards. And we're going to go ahead and instead of exposing any ports, we're going to link directly into this. Now you wouldn't do this for a production run, but for demo purposes, it's okay to have this in there. And I can see my demo page was returned from the container. Excellent. This is great, but now what about everything that we do within the container. Let's take a step back, and we know that the nginx container is based upon the Debian base image. So to keep everything sane, I'm just going to simply retag our original container image so that we can use it in the same manner for our second demonstration. Now though, I want to say, okay, how about instead of using Debian, let's use something like Alpine Linux in order to deploy this. Well, I've built a Dockerfile here that has that. And as we can see, the only change here is that we specified a tag of Alpine. We're still copying the same configuration and the same files, and we're still exposing on the same port. So let's go ahead and build that. Just give it a special tag name so that we can track it. And there we go. We've preloaded the Alpine image, and now we have a base container based off of Alpine. Let's take a look at all of our images thus far. As we can see, our base Debian image, the one we used from Demo 1, is 109 megabytes in size. It's a pretty hefty image. It's not horrible, but it's a pretty big size of that. Simply by switching, though, to the Alpine image, we reduce that down to 16.1 meg. That's a pretty decent savings for only switching out what base image we were using. But I think we can also do better. Let's say instead of using nginx, let's build our own custom web server out of Golang, for example. If you're not familiar with Go, this is not too hard to understand. Basically, we're creating a main function. We're specifying a handler that's going to simply write out our static website string. And then we're saying, listen for everything that comes into that web server on / or the root handler. And then listen on network port 8080. That's great. So let's see what we would do for our Dockerfile if we were going to use a static built binary like Go. In this case, our Dockerfile starts to get a little longer. I'm sorry, wrong one. I mentioned before we wanted to use from scratch images, but when we start out, we're actually starting out with a from Golang as a builder image. What we're using here is called a multi-stage build, which is effectively we're going to create multiple containers in the process of getting to this build process. Docker in this build process will only keep the last image you build and tag that one. So what we're doing is we're basically sending in all of our Golang compilers and everything that we need to build the application. We're copying in our Go code, and then we're doing a build process on it. Then we're going to keep that container as is, and we're going to start with our now from scratch container, which again is our blank container. We're going to copy in our built binary from the previous container, and we're going to say when this container runs, launch only that, and of course expose on 8080. The previous container will be destroyed, and we will only keep that last container, which only contains the rootfs and as well as our application binary. Let's go ahead and build that. This one should take a little bit longer, but not too bad as it goes ahead and builds the application. And as you can see in the top right, it was showing the actual processes needed to actually build that. Now, if we look and compare the three different image sizes, our from scratch image is only 6.57 megabytes. It's even more than 50% savings over the Alpine, which was already pretty small. Now, to prove that these are all the same, let's go ahead and run each one of these and show that we're getting the same result. First one second one, and our third one. As you can see, we've got multiple processes running here, and each one of them shows that we've got each one of our containers running. It's a little difference in how they're executed, but we do have the same functionality running, and we can test that by using our curl command again. We'll start out with a Debian. There's our website for first one. Then move over to Alpine. And lastly, our from scratch container. Look at that. 3 different image sizes where we're able to reduce the attack surface by not having any of the additional binaries that were unneeded for that, and able to reduce the size of the container sets much more easily able to be pulled even over smaller connections. But we still get the same result every time with running our containers. Just for right now, I'm going to go ahead and clean this up as we move on, and let's take a look at what we can do now with the users. So I mentioned before that you should always give a container a user. And by default, and even on my first 2 examples, I did not. Well, shame on me for that. Let's now look at what we would take. So we'll go back to our nginx example, still running on Debian, still got our same configuration, and we're going to add in this new section. Well, I've created a separate nginx.conf, which actually removes the user directive. And if you take a look at our nginx up in the top right here, the container has a master process running as root, but it has a worker process running as user 101. That is a configuration item that's in nginx.conf. Now, the worker process surely runs as a non-root user, but I also see that master process is running as root, and that's something I'd like to avoid as well. So my nginx conf simply has that user statement removed, and it will use whatever user the container is launched as. I'm then adding some additional information. In order for nginx to function, it does require certain directories to be created, and will only use those particular directories for write, and we can simply extend those into the environment for where we are now, meaning we're just going to bridge those volumes into the actual container as part of this process. And then, of course, we're specifying in user 1000. And this is just an arbitrary user selected. In the case for my EC2 instance, this will mean that we're going to select the EC2 user for these tasks that we're going to run. Let's go ahead and get started with this. I'm going to start the build process. Won't take very long. And again, it's reusing some of the layers that we have in here as well. It doesn't need all those layers to be started with. Go ahead and run this now. There we go. Now, let's take a look on the right. For our containers, we have demo 1 and demo 3. And short of the fact that they're using different images, we can't tell too much difference about it. But look at the timing here of this one being up 15, 16 seconds, and look now at our processes that are running. We can see based on this elapsed time that the processes that we're running now, these 2 new processes up at the top, are our latest container. And look at the user field. Instead of being launched by root, it's now launched as EC2 user, including that nginx master process. This means that my container no longer has any additional privileges and has the privileges of a normal user inside the host. Therefore, it's not able to elevate or to do anything that we wouldn't want it to do at this particular point. Let's jump back now into the presentation. So now that we have our container image, we now need a place to store it. And for that, we have container registries. Registries are simply that, a place to store container images so that they can be pulled by a runtime later. There are three main flavors we look at: private registries, public registries, and marketplace registries. Let's examine each one of these. Private registries can be trusted as long as it's yours or you trust who owns the private registry itself. These are important for making sure that you have a copy of your container image that's very close to a runtime. This helps to eliminate things like man-in-the-middle attacks or possibly trying to change the container image on the path. This also allows you to have a controlled maintenance window that you're in control of and not provided by some third party. It's also important to make sure that even if you're not using a private registry as your main source of truth, that you keep a cached image copy in AWS, such as in Elastic Container Registry, even if it's not the original. This helps to make sure that you keep latency down and further prevent those attacks. On the counterpoint, public registries should not be trusted. There are many cases in which a container image was published that also had a Bitcoin miner but used a common name like nginx. These containers were downloaded over 5 million times and resulted in revenue being generated in the form of Bitcoin using your own container images without your knowledge. Thus, it's very important to make sure that you understand where your registries come from and your images come from, and use trusted registries. Now, there is an exception to the public registries rule, and that's that Docker Hub has official repositories, which are what they consider essential base operating system repositories and software repositories that contain popular runtimes, data stores, and other services that you may use. These container images are curated and maintained by Docker Hub themselves and are also security scanned and updated by Docker. You can see more of these on the Docker Hub website below. A third option for pulling your container images is to use a marketplace registry such as AWS Marketplace for containers. This enables you to go through and find vendors that have provided their own container images. These container images have been curated and maintained by that particular vendor and typically done by the owner of the software. So nginx for nginx, Elastic for both Elasticsearch and Kibana, and so on. Inside the AWS Marketplace for containers, you'll also find software as a service products to help you manage, monitor, and protect your container applications and deploy them on AWS Fargate. Let's now take a look at how network functions within AWS Fargate. With a traditional instance, each instance would be given at least one Elastic Network Interface, or ENI, and that ENI would bridge the traffic over to each task and container inside of it. With Fargate, there is no instance, and thus we're creating a namespace around each Fargate task that gives each task its own ENI. This allows us to route directly to the ENI for the task and does not require changes to our VPC, though this does not work with dedicated VPCs. This also means that you can give each task its own security group and specify isolated rules on what network traffic is allowed in or out to a particular container or task. The task networking uses the standard CNI plugin architecture, which is an open standard for creating container network interfaces, and also uses an isolated network namespace inside of the Docker host per task. And in case you want to keep all of that traffic completely private and off of the internet, you're able to create a VPC endpoint with Elastic Container Registry, which allows you to pull the container images from within your VPC. This is supported with Fargate, meaning your Fargate pull all the way to completion can be completely contained within a VPC and does not have to be exposed to the internet. An example of configuring the AWS VPC mode for your Fargate task, and this is required for all Fargate tasks, is inside your task definition to specify the network node as AWS VPC. And then whenever you are creating or updating your service or creating task, you will specify the security groups and the subnets that belong as part of that, as well as whether you want to assign a public IP or not. Let's now take a look at authentication and authorization inside Fargate. There are a few different rules that you need to watch inside of AWS Fargate and ECS in general. The first is the task role. This is an IAM role that we are granting on a per task that gives each task its own set of permissions. These tasks are then able to access other AWS services, similar to how an AWS IAM user would access those same services. The second role is a task execution role. This role is used specifically by the ECS and Fargate service in order to pull container images or publish the container logs to Amazon CloudWatch. By assigning an IAM role to each task, we're able to isolate what permissions are enabled for each task and ensure that only the right tasks are able to get to the right AWS services. In this example, the top task has a role which allows it to get to a database, whereas the bottom task has a role allowing it to get to an S3 bucket and to a queue of traffic. Note that both tasks cannot see all the AWS services unless they have a role with the appropriate permissions. When configuring your IAM role, you do not have to make any difference versus that of an EC2 role to the actual access policy, but you do need to change the trust relationship. In CLI form, this is by specifying who is allowed to assume this role on behalf of the AWS service. We need to make sure and add in ecs-tasks.amazonaws.com in order to use this as a task role within ECS. You are able to use these roles with both ECS and EC2, but you can also strip away the EC2 permissions, leaving this task role to be only used by the ECS service. When developing your container images locally, it's commonplace that you would inject environment variables into your container image in order to pass things such as passwords, configuration data, and endpoints into your application. This allows you to have a single container image that works across multiple environments, but doesn't scale as you continue to add environment variables to the mix. You can use ECS and Fargate to configure environment variables inside of your task definition, but this also would expose any potential passwords that exist to anyone that has authorization to see that task definition. Thus, a better solution is to move to a password and secret managed store, such as AWS Parameter Store and AWS Secrets Manager. Both are backed with encryption by AWS KMS, and both offer very granular permissions as to who and what is allowed to pull those particular parameters and secrets using AWS IAM and your task role. AWS Secrets Manager has an additional benefit of being set up to do secret rotation dynamically so that you're able to automatically rotate your passwords without having to be concerned about what they are, only that they work and that your tasks are able to access the right services. Moving forward now, let's look at some different patterns for runtime protection. Whenever we started building applications on top of EC2, we always had a user and an instance, and we needed to make sure that that user could get to the instance. But we wanted to make sure we had certain controls, such as a firewall or security group, to ensure that we had the correct network permissions. And we always had an agent on the instance that was able to do monitoring and alerting if anything were to change outside the standard. When we move to ECS with EC2 launch type, the instance gets a little bit bigger as we need to start hosting containers inside of it. But the access pattern doesn't change. We still have a user who's going to access those tasks. That allows us to still use a firewall or a security group in order to maintain the traffic flow, and we're able to place an agent onto the instance that's able to monitor the containers and tasks from a singular viewpoint. But how does this work when we start looking at ECS running on Fargate launch type? There is no instance to configure. Our user is still able to get to the tasks and containers, and we're still able to put a firewall or security group in order to protect that traffic. But what do we do with the agent? We've come across two main patterns that we see for actually deploying an agent that works within Fargate. The first is to place the agent inside the container by building a task definition with a single container, and that single container contains both your application code and the agent code, which run in parallel. The other option that we've seen is to use a sidecar container, whereas you create a single task definition that has a container with both your application code and a second container which contains the agent code itself. Now let's take a look at some advanced features that we have available to us with AWS Fargate. The first of which is the ability to reduce or remove the Linux capabilities. With Linux, most containers and most processes do not need root privileges. Logging can be handled through the runtime. The network is automatically managed for the container. And if we're using immutable containers, we do not need to remote in to that particular container. Docker by default will automatically drop many of the capabilities that Linux provides as unnecessary. This helps to reduce the blast radius in case the container has been compromised by an outside source. And you're able to further reduce this list by removing some of these additional capabilities. Because we are not able to add any of these capabilities back, you are not able to create privileged containers as a result, which is an additional security benefit. In order to specify the capabilities that we're going to remove, you simply create it into your task definitions further inside the container definition. You'll specify which capabilities you want to drop using this format. The next feature are what we call resource limits or user limits. These are operating system level features that are guideposts for how much resource you can use inside of a particular operating system. From the number of cores that are able to be used, from the number of file locks that can be taken, to the blocks of memory that can be used, to the number of processes that can be run. Docker takes further use of this by restricting the use of resources per container in what we call a per process limit or PR limit. Within ECS and Fargate, we're able to specify both a soft and a hard limit per resource. Soft limits can be increased by the container should the operating system of that container ask for it, but hard limits cannot be increased by the container. In order to increase a hard limit, you would have to change the task definition and restart the task or service. An example of using resource limits is to look at the number of processes that are able to be run inside of a task. Suppose you have a process that starts another process, and that second process starts a third, and that third process starts a fourth. This is what often has been referred to as a fork bomb, because each process forks another until the computer behind it is unable to handle the request due to so many processes running. This is very much a denial of service scenario that can be easily prevented by specifying a hard limit on the number of processes that are able to be run. Let's take a look and see how that would be done. Within our task definition, we're able to specify the ulimits inside the container definition section by naming each limit that we want to restrict and specifying both the soft limit and hard limit. In this case, I've set a soft limit of 20 and a hard limit of 30, meaning that the task and container inside the task will be able to spawn 20 processes without problem, and we'll be able to request up to 30 processes from the host before it will fail the container for trying to request too many processes. Now, with the immutable infrastructure that everyone can use today, there becomes a case where you may not need to actually write anything to the container file system. Any changes that you can make to your application will be pushed in from a future file that you have. And all of your logs are able to be written out via standard out and standard error. Thus, there's the ability to specify in the task definition that we want a read-only container. This creates the file system so that it's unable to write files to it, meaning that if the container is compromised, this means that someone could not go into your website and add additional material that you do not want present, or that someone could change something in your batch process without you knowing. Again, this is best fit for immutable workloads. If something has to change within the application, simply relaunch a new container. In order to configure read-only containers inside the task definition and further inside the container definition, you simply only need to set the read-only root file system property to true. Now let's take a look at how we can use resource limits and read-only containers within AWS Fargate. Jump back over to our terminal. I'm just going to start by running a standard Amazon Linux container, which I've already preloaded the image. Now, first thing I notice is this container is running as root. We'll get to that in a second. But what I'm after finding out is whether this has any process limits involved on it. The command we use for that is ulimit, and specifically looking at the -u means number of processes. Off the bat, I can see that's unlimited, and yeah, that's kind of scary. So let's not go ahead and set off a rabbit here. Exit as container, I want to set a limit at runtime. Now keep in mind I'm doing this on my local laptop so that we can actually see the results of what's happening per process, and we'll demonstrate this on Fargate in just a minute. Take our command, and I'm going to say we're going to set a soft limit of 5 and a hard limit of 10. Okay. So we launch our container, and we can now see that we have different, the S means soft, we have different process limits, and capital H means hard. There. It accepted our runtime parameters for how many number of processes we're going to allow. However, this container is root, and as we mentioned, a hard limit on container can be increased by someone with privilege. And since this container is running as root, if I were to set off the fork bomb now, it would still crash my demo machine and prove to have a very bad afternoon for us. So let's exit out of this, and let's again give this just one more property at the runtime. We're going to set a user that does not have elevated permissions when we run this. There. Now my container from the top right we can see is running as nobody. And if I do my ulimit checks again, I can see they only have a certain number of processes. So now let's go ahead and build this. If you want to, you could always Google the process for actually creating this. But basically what I'm going to do is I'm going to create a function inside Bash that will either run itself or it will run itself and then stick itself in the background. This function is now live, and all I have to do to set it off is type fork bomb. Now look at the right exactly what happens. We automatically spun up from the first process to the other 5 processes, and it's continuing to try and spawn more processes, but it's either getting a response of resource temporarily unavailable or no child processes. I have therefore very quickly and very easily prevented a fork bomb from going off inside my container and compromising my demo machine. Now, we'll just kick out of that for a second. I did mention that soft limits can also be increased by inside the container. So let's simulate that. I'm going to say I want to set the soft limit to 10. And we'll go ahead and run that off again. What happens? We'll look on the right. We get up to 5 processes, but we're still managing to stop all the other processes from spinning up. And you can see that there's some tree hierarchy here as some of the sub-processes spun up processes as well. That would continue normally until there was nothing left to do. But as you can see, it's been prevented here. So let's go ahead and stop that, and just to show it, let's go ahead and try and say, I want to set the hard limit up higher. Oop. Looks like it's still trying to exit out. I'm going to set it to 20. Oh, wait a second. My max number of user processes. I am not permitted to increase a hard limit. As we mentioned, it requires privilege, and I'm thus running in a container which does not have sufficient privileges to increase the number of processes. Now we can also take that fork bomb and we can also stick it into a container itself. Let's go ahead and take a look. I've kind of preloaded that. We're specifying Amazon Linux. We're going ahead and setting an arbitrary user. And when I go ahead from my build process, I'm going to set a ulimit. Those won't survive when we actually go to run the container, but they will stick around. And thus, whenever the container is launched, I'm going to say, okay, start a shell prompt. We're going to create and then launch our fork bomb, but we're only going to give it 10 seconds. So we're going to set this off, and it's only going to last for 10 seconds. Once a command has finished, the container will exit. And fork bomb does not technically keep the main process into a shell. So therefore, it will exit after about 10 seconds. So we can go ahead and build this one. We'll use 04. There we go. And for fun, we're going to detonate it inside of our environment right now. Keep it in the front, it won't matter. Well, that didn't go well. I missed a few steps, and therefore I actually crashed my demo machine. As we can tell, it was able to still elevate some permissions. So let's go ahead and let's add in the pieces that we are missing. So we're going to, again, use a nobody user, and we're going to restrict it to just 5 as a soft limit and 10 as a hard limit for processes. And when we run it, we can see it gets stuck with just the amount of processes that we have. It's, of course, going to keep trying and forking those processes, find out it's not able to, and then after 10 seconds, just exit out. That's great, but this is a Fargate class. So let's take a look at exactly how we would do this inside of Fargate. For one, I'm going to need a few resources, and let's just see if these exist already. All right, and let's go ahead and get a repository. Nope, already have a repository. That's okay. Now I'm going to copy something over. This is just a quick script to take the repository URI from our repository and set it as a variable named repo. As we can see, we now have the actual repository name that we're going to use. This will become the image name and the repository name and the registry name, and the only thing that's missing here is the tag. Now let's go ahead and log in to ECR. And I don't care about any errors. We'll just safely ignore them. All right. Now I want to take all the images that we built right now, and let's just go ahead and stick them up in the ECR, and that way we've got access to them. So to do that, we can use a simple bash script. And we're basically just going to tag them all with that, have that tag, and we're going to retag them to use the repo. There. Now if I do a list of all the container images that have that, I can see that they have now all been retagged or added additional tags locally so that they match my repo format. Now, let's just stick them up in the repo. Shouldn't take more than a few seconds, but all we're doing is it's taking all the different layers, it's smashing them together, and it's sticking them up into Amazon ECR. That way, I have access to actually get to them when I need them. As we can see, some of them are already created too. Next up, we're going to make sure, and I've already created a task definition that contains everything we need for launching off the rabbit inside of AWS ECR and inside of Fargate. So let's go ahead and take a look at that task definition. As you can see, I've named it Fork Bomb. We're on revision 2. And all I'm really interested in is the container definitions portion. So let's take a look at that container. Yep. So as you can see, arbitrarily put a memory reservation. We've named the container inside the task definition as demo_04. And we are using the demo_04 image that we just created back locally. We're also going to be sending these logs to an AWS log group called ECS Fork Bomb, and that's so that we can retrieve the logs later and verify that this works. In addition, we've set the ulimits for number of processes to 5 and 10. So now let's go ahead and run a task and see exactly what we get. I've copied in a lot of this, but we can go ahead and read through some of it. Basically, we're going to be launching in our demo cluster using our Fork Bomb task definition, and we're using Fargate. Everything else that was specified is just simply subnets and security groups so that it can run successfully. And it did run and is probably in the provisioning state now. So the key thing that we're going to need here is going to be our task ID. So I'm going to go ahead and create another environment variable that has our task ID. That way we have it for later. Now, let's go ahead and see what the status is of our current running task. Sorry. Nope, looks like our task is already exited. Okay. Well, we did manage to grab the task ID, so let's go ahead. Got one other statement we're going to copy in here. As you can see, I want to get the log events that happen from that particular task. We're specifying the log name, we're specifying the log stream name, and we're going to go ahead and use that variable we just created of task ID in order to get the logs from it. And as you can see, we had the same output that we had from our console when we were running it locally, that we were able to successfully prevent the number of processes from greatly exceeding the amount that we specified, and thus preventing a fork bomb. Let's now move into launching a read-only container as well. In order to start, nginx does require a few folders, so I'm going to go ahead and just copy in the commands to create those now. And I want to go ahead and get our control task running, so I'm going to go ahead and launch locally demo01, so it's back up and running again. Now, I want to use this same container, or this same container image, but specify it as read-only. So in order to do that, I'm going to use the same commands. I'm going to go ahead and use the same image, except I'm going to give it a name of demo05. And I'm going to specify read-only. I mentioned before that nginx has a very special way that it has to run, and that it needs access to a var cache nginx and var run to be writable, even with a read-only container. The way that we do that is by using local forwarding of volumes in order to give those two volumes inside the container write access. Note that this is special to nginx, and if your software has a component like that, you can still restrict it because var cache nginx and var run are often not accessible by a web server host itself. Finally, we're going to specify to use our original container. And off and running, we now have a demo 05 container that's running as well. So why are read-only containers good? Well, for one, we want to make sure that something is not writable. So let's take a look real quick at our demo 1 container. If I were to run our curl statement, I'm going to go ahead and paste this one in. We see that we still get the same demo page that we had before. What happens if someone is able to somehow compromise this container? Like having the passwords or being running on the host or compromise the host itself. I suddenly get into the container and I can add a bad message into our container and replace the file that contains index.html. Now, when I run my container again, our container's been compromised. That's not good. So let's try and do the same thing with our demo 5 container. All right, to start, we do get the same page. Let's somehow get into the container, assuming that they're able to break in. All right, I was able to get in. Let's go ahead and put the same statement through. Oh, instead, I get an error message back. Wait, this is a read-only file system. You are unable to make those changes. Therefore, if I go back and I try and look at our original file, we can clearly see that we still have the demo page. Thus, by using read-only containers, you're able to prevent someone who's able to break into your container and suddenly change something to show a website that you did not intend to in the first place. Let's conclude our demo and go back to the presentation. As we wrap up, Fargate has added a number of compliances and certifications which help you to build stronger, more secure applications on AWS. From PCI and HIPAA, which enable our customers to be PCI and HIPAA compliant, to the ISO 9001, 27001, 27017, and 27018, as well as the SOC 1, SOC 2, SOC 3, IMDA, and other certificates. For more details, please visit the AWS compliance page. Fargate also has a service level agreement where we strive for 99.99% or 4 nines of availability for your Fargate running tasks. Fargate has also recently announced a price reduction. As of January 7, 2019, we have reduced the price for Fargate tasks by up to 50%. We have reduced the price of virtual CPUs by 20% and the price of memory by 65%, both at a per second granularity. This is the result of improving efficiency for projects like Firecracker. Thank you very much, and thank you for watching this broadcast.